So I'm going to work through this problem slowly now in pieces. Each time that I show you something that you got stuck on before, I strongly recommend you pause the video and then see if you can finish it off from there. So that way you'll really be able to sort of put this stuff into practice when you're going. But if you get stuck again, just wait for the video to catch up and you can move on. Okay, so why is this soap bubble going to make a particular shape at all? The answer is that the bubble is going to try and minimize its energy, and that's going to be when it minimizes its area. So its total surface area is the thing that's going to have to minimize. And that makes it a calculus of variations problem, of course. And we're going to work out the area by adding up, breaking this area, this soap bubble up into lots of little pieces, and adding them up. Now, in order to calculate this area element, we're going to employ a very powerful principle, the principle of symmetry. Because this problem is completely symmetric around this axis, the axis of generation, we're going to assume that the solution is also symmetric with respect to that axis. Indeed, that's an assumption, but it happens to be true in this case, and it's often a very good piece of intuition. Now, if it's symmetric, then in fact, the shape is always a circle. So it's a circle, a very badly drawn circle, but I've got lots of perspective here. So this thing's always just a kind of a tube, and the only question really is how big is the tube? And the radius of the tube is defined by one line, by its radius. And so for each point in between these two, all I need to know is one number. In other words, it's defined fully by one function, the function where we've got a y of x, and I've defined some kind of x-axis. Okay, so all I have to do is work out the area in terms of that function y of x. Have a go at that. Now, in order to do that well, what we do is we break up our area into pieces. So we pick a particular x, and we have a very thin piece here. It's thin, but of course it's a circle. Because the thing can be on a very strong slope, that width there is ds. And its total area is going to be the circumference of the circle times its width. So it's going to be 2 pi times y, that's the circumference of the circle, and its width is ds. That ds, we can take the 2 pi out of the integral. That ds, as we've shown several times before, is just 1 plus y dot squared dx. And suddenly we have the area. We have the area in terms of y and y dot. And so all we have to do is maximize this. And of course, maximizing this whole thing is the same as maximizing it without that. So we don't have to worry about the 2 pi. Now we can solve this using the Euler-Lagrange equation, or we could use the Beltrami identity, because this again does not depend on x so explicitly. So the Beltrami identity is that y dot delta f delta y dot minus f is some kind of constant, and we can calculate that. Y dot, we've got a y of x, we've got this derivative with respect to y dot, minus a half, chain rule, we've got a 2y dot popping out of that, minus our f equals k. Some of these cancel. They cancel, and we end up with y dot squared. We've got a y. We've also, if we take out a factor of 1 plus y dot squared on the bottom, we get a y dot squared minus a y, one of those squared, which you'll notice has actually worked very well because the y dot squareds have cancelled, so we've just got a y on square root 1 plus y dot squared equals minus k. And the minus sign doesn't matter much because k was some arbitrary constant in the first place. So this is the equation we have to solve. We could do it by rearranging and try and getting all the dy and y terms on one side and the x on the other and integrating, and that would work. But taking into account the fact that we don't enjoy doing such things, now is probably the perfect time to get a computer on board. So what I've done here is I've taken my favorite program, Mathematica, and I've plugged in the differential equation indirectly into dsolve. Dsolve solves differential equations analytically. So I've got my y of x and my square root 1 plus y dash squared equals some constant. Note the double equals, don't forget to do that. and I'm solving for this function, and this is my variable. I hit return and out pops my answer. And you can see I've got two possible answers here. They've both got exponentials in them, and they're multiplied by sums of exponentials. And sums of exponentials like that are basically shines and koshes. The correct solution, which gets rid of this constant here, the C1 that came, the constant of integration that came in, and the K, is where you put in the boundary conditions, which says basically how big the actual rings are, and so it gives you two values of Y at two different positions in X. Okay, but what does all that look like? Let's have a look. It looks like a soap bubble. There's our soap bubble. And as you can see, it's making a beautiful soap bubble kind of shape. When the rings are very close to each other, then the soap bubble shape is almost a cylinder. You can see that it does bow in a little bit, but basically as we make that closer and closer and closer, all it needs to do is make a little ring. And so it makes a cylindrical type shape. But as the rings get further and further apart, then it really dips in badly in the middle. The reason it does that is that covering across here, it's got a great big radius to make an area, whereas if it dips in there, it makes a lot of surface area through this bit, but then this bit's very cheap. So all this extra distance in the middle, it gets away with very little surface area. And if you go too extreme, of course, the solution becomes pathological, and the actual solution is I'll make a big soap bubble on one side, a big soap bubble on the other ring, and have an infinitesimal line in between them. And if you go to that limit physically, what happens, of course, is that the soap bubble breaks. But in between, we have a full solution that we can work out.